ever stop to think about it? Every single thing around you, the building you're in, the chair you're on, even your phone, is constantly being pushed and pulled by invisible forces. So how on earth do we design things that don't just, fall apart? Well, it all starts with a system, a way to organize that chaos, and that's exactly what we're going to break down today.
Right? Take a look at any bridge. It's a battlefield of forces. To have any hope of predicting whether that bridge will stand for a century or fail spectacularly, engineers need a shared language, a way to describe all those pushes and pulls. It all begins with classification. So, here's our game plan. First, we're going to give a proper name to this whole chaos of forces. Then we'll split them into two big categories, before getting into the three most common types you'll see. After that, we'll talk about a really cool shortcut called transmissibility, and then we'll tie it all together to see why this stuff really matters in the real world.
All right, let's jump right in. What do we even call this collection of different forces all acting on one object?
We call it a system of forces. Simple enough, right? But this isn't just about making a list. It's all about how those forces are arranged geometrically. Are their lines all pointing to the same spot? Are they running parallel to each other? Or is it just a complete mess? Answering that question is the key to pretty much everything that comes next. Now, the very first move you make when you're classifying a system of forces is to ask one super simple question. And the answer splits the entire world of mechanics right down the middle. That's it. Is this a 2D problem, something you could draw on a piece of paper, or is it a 3D problem that exists in the space all around us? In engineering speak, we call these coplanar and non-coplanar systems. Let's see what that actually looks like. And here's that split visualized perfectly. Over on the left, you've got a coplanar system. See how all those forces, F1, F2, and so on, all live on that one flat XY plane? But on the right, you've got a non-coplanar system, sometimes called space forces, where they're acting in full 3D. Now, while the real world is obviously 3D, a ton of problems can actually be simplified down to 2D. So for our purposes today, we're going to stay in that coplanar world. So let's lock that in. A coplanar system just means all the forces are happening on a single 2D plane. Got it? Good. Now let's get a little more specific. Okay, so once we know we're working in 2D on a single plane, we can break things down even more. It turns out there are three main types that cover just about every situation you're going to run into. First up, we have the concurrent system. The keyword here is concur, like to agree or come together. And that's what these forces do. If you imagine drawing a line through each force arrow, extending it forever, well, in a concurrent system, all those lines would cross at one single point. Check out the lamp. The tension from the wires and the weight of the lamp itself all meet right there at point A. It's a really clean and common setup. Our second type is the parallel system. And yeah, it's exactly what it sounds like. All the forces are parallel to each other. Think about the Vender's scale. The weights are both pulling straight down. Or the people sitting on the bench. Their weight pushes down and the legs of the bench push up from the ground. All those forces are running in parallel lines, super common.
And finally, we have the catch-all category, the general system. Basically, if the forces don't all meet at one point and they aren't all parallel, they get tossed into this bucket. Look at this plate here. You've got forces coming in from all different directions at different spots. This is definitely the most complex of the three, but hey, the real world is often messy, and this system describes a lot of it.
Okay, so we've got our classification system down. Now let's talk about a super powerful rule that helps engineers simplify all of this stuff. It's called the principle of transmissibility. All right, that's the textbook definition. I know it sounds a little dense, but the idea behind it is actually incredibly simple and really useful. Let's break that down into plain English.
Here it is. All that definition means is that you can take a force and just slide it anywhere you want along its line of action, and it won't change the overall effect on the object. Now, there is one major catch here. This only works if we assume we're dealing with a rigid body, something that doesn't bend, stretch, or deform. Let's look at a classic example that makes this crystal clear. The train. This is perfect. Think about it. To get the whole train moving, does it really matter if the engine is at the front, pulling the first car, or if it was at the back, pushing the last car? Nope. As long as the force is the same, and along that same line, the overall result, the whole train chugging forward, is exactly the same. That force is just transmitted through the train. This little trick is a huge time saver for engineers. So, we've organized forces, we've put them into nice, neat categories, and we've learned a key principle for simplifying them.
But let's zoom out for a second and ask the big question. Why do we go through all this trouble in the first place?
Because this framework, this is the language of engineering. It's how you take that chaotic mess of forces we started with and turn it into an elegant problem you can actually solve. Before you can even begin to calculate the stress on a bridge or figure out the lift on an airplane wing, you absolutely have to ask, what kind of system am I looking at? Getting that classification right is the essential, non-negotiable first step to designing things that are safe and that actually work.
And that kind of leads us to a final thought. We've learned how to sort and label all the forces acting on an object. But what happens in that special, perfect case, where all those pushes and pulls completely cancel each other out? What happens when you have a state of perfect balance? Well, that state is called equilibrium, and it's the secret to how every stable structure around us stands up. But that's a story for another time. Thanks for joining me.